Okay, so we can start.
Yeah.
So it's a pleasure to introduce Michela Artebani from Universidad de Concepción, who will give our last talk of today about Cox rings of K3 surfaces.
Thank you a lot for the invitation, and sorry for the problem here. So I'm going to talk about Cox rings of K3 surfaces. This is a joint work with Claudia Correa Deisler from Universidad de Concepción, Antonio Laface, again from Universidad de Concepción, and Xavier Rollot from Marseille University. So, so the idea of the talk is, first of all, I would like to introduce some basic language on Cox rings, and then I will concentrate on the case of K3 surfaces, and I will try to tell you about some results on the degrees of the Cox rings of K3 surfaces with the finite automorphism group. So let's start with some definitions. So the definition of Cox ring is quite general. So let's take X to be a normal projective variety, let's say over the complex numbers. In this definition, I will assume that the divisor class group of the variety is finitely generated and free, even if, well, this can be also relaxed. And in particular, I will fix a certain subgroup of the group of Weil divisors on the variety, and an isomorphism between this subgroup and the divisor class group. So we fix this in this setting. I can define the Cox ring of X in the following way. It is an algebra which is graded over the group K. And it is the direct sum of essentially of all Riemann-Roch spaces associated to elements of K. Actually, well, it can be proved that the different choices of the group K, which is isomorphic to the divisor class group, lead to isomorphic graded algebras. So this is independent of this choice. Well, if you look at a homogeneous element of this ring, this is nothing but a rational function which belongs to some fixed Riemann-Roch space associated to some D which is a divisor in K. I will say that the degree of such an element is the class of D in the divisor class group. Okay, so the homogeneous element is a rational function, but associated to a certain class in the divisor class group. Another important point is that to any effective divisor on the variety, one can associate essentially a unique homogeneous element in the Cox ring up to a constant in the following way. So let's say that E is an effective divisor on X. Then, of course, there is a unique element D in K, which is linearly equivalent to E, because we said that the class map from K to the divisor class group is an isomorphism. And we choose F as the rational function which defines this linear equivalence. So F is an element of this Riemann-Roch space associated to D, and the divisor of F plus D is equal to E. So it is unique up to scalar multiplication. Yeah, so to an effective divisor, one can associate an homogeneous element essentially of the ring. So why is this object so interesting? So of course, one from the definition, one can understand that it is a fundamental object associated to the variety, because essentially it codifies all possible maps from the variety to projective space. More precisely, it is interesting the case when this ring is a finitely generated algebra over the complex numbers. And in this case, the variety is called to be a Mauridrin space. I will explain in a moment why the reason of this name. So in this specific case, so when this is finitely generated, there are two interesting properties of the variety. First of all, it happens that if one considers the effective cone over Q, so it is the cone generated by effective divisor in the divisor class group tensor Q, this cone is polyhedral. And more precisely, what happens is that if one takes a finite homogeneous set of generators of the Cox string, and one looks at their degrees, which are classes in the divisor class group, these classes generate the effective semigroup. That is, any class of effective divisor can be written as a linear combination with the non-negative integer coefficients of these classes. And this comes essentially from what I said before. So I said that to an effective divisor, one can associate a homogeneous element. So these homogeneous elements can be written as a polynomial in some set of homogeneous generators of the ring. And if, in particular, if one takes degrees of this implies that the degree of F can be written as I said, as a linear combination with the non-negative integer coefficients of the degree of these generators. So it comes from this connection here. So this is, on one side, it is an interesting property. And a second very important property is that Moridrin spaces can be described as quotients of a certain open subset of the spectrum of the ring. So let me say it more precisely. Let's take the spectrum of the Cox ring. So this is an affine space. Let's call it X bar. There is a certain open subset of X bar, which is called X hat. What happens is that there is a torus acting on X bar and preserving this open subset. And if one takes the quotient of X hat by the action of this torus, one gets a morphism, and the quotient is essentially the original variety. So let me say it again. So the variety can be recovered as a quotient, a GAT quotient actually, by a torus action of an open subset in the affine variety associated to the Cox ring. So the easiest example of this is the usual standard construction of the projective space as a quotient of, let's say, C to the n+1 minus the origin. So it is an open subset in C to the n+1, and it is the quotient by the action of a one-dimensional torus. The dimension of the torus actually is coincides with the rank of the divisor class group. So actually the torus is the spectrum of the group algebra associated to the divisor class group. So there is this very nice construction in case the Cox ring is finitely generated. So a natural question is it true that the Cox ring determines the variety? And the answer in general is no. So in general, the Cox ring does not identify X. And the reason is essentially that this open subset X hat can be chosen in different ways. And there is actually what is called a variation of GAT. And different choices of this open subset give rise to different quotients, which have the same Cox ring. Actually, if one thinks to it, if one takes two varieties which are birational, which have a birational isomorphism between them, which is an isomorphism in codimension 1, so they have the same kind of same divisors, then it is clear that the Cox rings are the same because of the definition of the Cox ring. So in general, it is not true. However, in some cases, for example, in low dimension for normal projective Moridrin surfaces, this is true. So normal projective Moridrin surfaces with the same Cox ring, of course, isomorphic as graded algebras, are isomorphic surfaces. So this object really, in that case, does identify the surface. Let me tell you something about what is known, some known examples of smooth projective Maury-Dream surfaces. A first important class is given by rational surfaces with big anticanonical divisor. This is a result by Testa, Varilli, Alvarado, and Velasco of 2009. Among these surfaces, you can think of toric surfaces and to Del Pezzo surfaces, for example. Actually, I'm giving examples only in the case of surfaces, but let me say that in general, toric varieties are the first example of Maury-Dream spaces. And it can be proved that for them, the Cox ring is actually a polynomial ring. So they are the kind of first step for the study of Cox rings. A second class of known Maury-Dream surfaces are rational surfaces with such that the Kodaira dimension of the anticanonical class is 1 and having a finite number of -1 curves. This is a joint result with Antonio Laface. For example, in this class, you can think of extremal rational Jacobian elliptic surfaces with a finite number of -1 curves. That is where the Mordevai group is finite, for example. We also have C-star surfaces. So if we take surfaces acted by a torus, which is not two-dimensional as in the toric case, but one-dimensional. This is also a result of Ausensus in 2010. And another class, which is actually the one I'm going to talk about, are K3 surfaces and also Rieke surfaces with finite automorphism group. This is a joint result with Ausen Laface, but it was proved more or less at the same time also by McKernan in 2010. So I will talk much more about the case of K3 surfaces in a moment. And lastly, let me mention that there are some recent examples by Kuhn and Lee for minimal surfaces of general type with PG equal to 0, which are Maury-Dream surfaces. So let me observe that the property of being Maury-Dream in the case of surfaces actually depends more, as you see, on the Kodaira dimension of the anticanonical class and not on the Kodaira dimension. Actually, there are surfaces with the same Kodaira dimension, and one is finitely generated Cox ring and the other is not. Just think to the projective plane and blow it up and 9 general points, for example, and this is not a Maury-Dream surface anymore. So it comes out from the results in the literature that the anticanonical Kodaira dimension is the most interesting invariant for this. Are there any questions so far?
Yes, there was a question in the chat. I don't know.
Hi, Michela. Yes, I asked the question. The morphism P from X at to X is not unique. This one, there is a morphism P.
Yes, I mean, if you fix the open subset, then it is yes, because you have an action of the torus on
Okay.
X bar. Yes. Yes. So the key point is the choice of this open subset.
Okay.
So if you start from the Cox ring, yes, you have to do this choice. And the fact, actually, I didn't say that, the fact that the X bar is acted by this torus is because the algebra is graded by the divisor class group. So there is a translation when you go from the graded algebra to its spectrum, the grading converts into a torus action. Yeah. Okay.
I have another question, sorry.
Yes.
You said that normal projective Mori dream surfaces are a class of surfaces for which that are identified by the Cox ring. But besides this class, there are other exceptional examples, or not
So
in the
actually,
family, I mean, not general, but something more is known?
let me say that actually it is an opportunity to say something more. So the reason why these are called Mori-Dream spaces is that actually this class of variety arises as something interesting in birational geometry.
Mm-hmm.
In this sense, I mean, it can be proved that this the choice of this open subset corresponds to a variation of GAT. So there are different ways to choose this semi-stable locus, and it can be proved that the chambers for this
Yes.
variation are the same as the Mori chambers for these varieties.
Ah, okay.
So if you know that there is a unique Mori chamber, for example, then
you know that
you can
it is.
reconstruct. Yes,
You
this
can.
is essentially.
Thank you very much.
This is essentially the point. Yes. There is the seminal work about this is the work by Wu and Kiel about Mori-Dream spaces,
Yes.
where they gave this connection between birational geometry and the finite generation of this algebra.
Mm-hmm.
Okay. Let me continue. So what I'm going to say, talk about, so the subject, of course, is very big. There are many things one can talk about, many open problems. Here, I'm interested in the problem of computing the ring. So let's say we have some result which says that the ring is finitely generated. I will say something more for K3 surfaces. I want to compute the ring. And compute the rings means, of course, to give a presentation of it. And in general, this is, I would say, a very difficult problem. And I will concentrate on the specific problem of finding generators, and more precisely finding the degrees of a homogeneous set of generators. One first remark about this is that the Cox rings needs generators in all the degrees of the Hilbert basis of the effective cone, sorry. And the reason for this is what I said before. So I said that if the variety is Mori-Dream, then the degrees of a set of homogeneous generators generate the semigroup, the effective semigroup, let's say. So among the generators, I need to have the degrees of a Hilbert basis of the effective cone. Otherwise, I could not generate the semigroup. So this is a first basic remark. For example, in a surface, all classes of -2 curves give rise to generators of the Cox ring because they are extremal rays of the effective cone. So I do need a homogeneous generator in that degree because of this fact. However, in general, so it is easy to see examples where these generators coming from negative curves are not enough. And in the case of surfaces, there are several examples of explicit computations of Cox rings. For example, we know actually in general how to describe the Cox ring of any normal toric variety. And as I said, this is a polynomial ring, and one can, let's say, relate the degrees of the generators to the fan structure of the fan associated to the toric variety. This is a result of Cox. Then there are explicit computation, talking about the generators for all the pezzo surfaces. This is a very nice paper by Batirev and Popov in 2002. We have a joint work with Alice Garbagnati and Antonio Laface when we compute the ring for extremal rational elliptic surfaces. There is a description of Cox ring of C-star surfaces by Hausen and Suess. And finally, there are some computation for K3 surfaces for Picard number 2 and for some double covers of smooth rational surfaces. The case of Picard number 2 is a work by Ottem, and the work about double covers of smooth rational surfaces is in a joint paper with Hausen and Laface. I would like to stress that in general, we use very ad hoc techniques. So techniques which really depend on the type of surfaces we are working on. The general idea I would like to convey later is that in the case at least of K3 surfaces, we are looking for a more general and more computational method to give at least a set of generators. Let me explain some basic techniques. So the first very simple idea, let's say, I'm talking about here the problem of identifying the degrees of a set of generators for a Mori dream surface, is the following. So this is a result which is actually contained in the book by about surfaces by Beauville. So let's take two effective divisors, E1 and E2, which have empty intersection. And let's take F1 and F2, two rational functions, which are defining section of E1 and E2 in the sense I said before. Then there is an extra sequence of shifts, which is the one you can see here. In particular, observe that the map phi is the one which sends G1, G2 to G1, F1 plus G2, F2. F1, F2 are these defining section of E1 and E2. So one can now take any effective divisor, let's say, on the surface of, actually this is also in higher dimension, and tensor the previous sequence with OXD, and then pass to cohomology. And what happens is that you get the direct sum of H0 of XD minus EI, which goes to H0 of XD. This is the map induced by phi. And then the next space is the H1 of D minus E1 minus E2. And this map from the direct sum to the H0 of XD is essentially the same I wrote for shifts above. So now a very easy remark is that if this H1 is equal to 0, then this map induced by phi is surjective. And what does it mean that this map is surjective? That any element of this H0 of XD can be written in terms of elements of this H0 of D minus EI plus these two elements F1, F2. So in particular, we can say that we don't need generators of the Cox ring in degree D, because any element there can be written using elements in different degrees. This is essentially the key ideas. Anytime you have this type of surjectivity with a map of this type, then you can say that you don't need to have a generator in degree D. This is the first example of a Koszul exact sequence. And this actually turns out to be very, very useful for many examples of surfaces to compute the generators of the Cox ring. Well, this can be actually generalized. So we did it in a joint paper with Claudia Correa, Antonio Laface, but I'm not sure this could also have been written somewhere in the literature, because essentially it is a generalization of just take a larger exact sequence. And it is a 3-term this time sequence. So take 3 effective divisor, E1, E2, E3, whose common intersection is empty. Take an effective divisor D. One can prove that if the H1 of D minus EI minus EJ is 0 for all E different from J, and the H2 of D minus the sum of the 3 is 0, then this map, which is the analogous of the previous one, is surjective. So again, if we have this vanishing, this cohomology vanishing, guarantee that so the surjectivity, and so we don't need generators in degree D. This is a fundamental idea. And actually, this is the key point of the theorem I'm going to tell you in a moment, which is about, which describes the degree of generating set of the Cox ring for any K3 surface. But before that, let me just recall that, so one, of course, point which makes it easier to deal with the K3 surfaces in this theory is the fact that the theory of linear systems for such surfaces is well established. For example, we know that if a divisor is NF, then the H1 is 0 unless D is a multiple for some alpha bigger or equal to 2 of the class of an elliptic curve. Moreover, we know that if an F divisor is always base point free, unless it is linear equivalent to, again, a multiple of an elliptic curve plus a -2 curve, where the -2 curve and the elliptic curve intersect at 1, and this alpha again is bigger or equal to 2. These are all quite classical results. And finally, let me mention that it is already known, it is contained in the paper by Sendona, what happens if I take a ray inside the Cox ring. So let's take just one divisor, more precisely a smooth irreducible curve, and look at the ray, let's say, given by the direct sum of the all Riemann-Roch spaces in degrees n times d. And it is already known that it is finitely generated, and it is generated in degrees at most 3, depending on the, actually depends, for example, whether the divisor is hyperelliptic or not. But in any case, you need to take generators up to n equal to 3. So the theorem we proved in the case of the K3 surfaces is the following. So let's take any complex projective K3 surface. Then the degrees of a minimal homogeneous generating set of the Cox ring are either classes of -2 curves. Actually, we know that all of them are necessary. Sums of at most 3 elements of the Hilbert basis of the NF cone, allowing repetitions of these elements in the Hilbert basis. So sums of at most 3 of them. And finally, there is a kind of exception. Generators whose class are of this type, twice the sum of 2 elliptic curves, which intersect at 2, intersection multiplicity 2. So let me stress that this holds for any complex projective K3 surfaces, so not necessarily Mori dream. Of course, if it is not Mori dream, we will have that, as I will actually explain in a moment, what happens is that in the class 2 or 3, we can have infinitely many classes. Okay, so we can have infinitely many classes of type 2 and 3, or 1 even, sorry, 1, 2, or 3. But again, so we can say that the Cox ring can be generated using only generators in such degrees. So this is the first remark. So it does not require X to be Mori dream. Second, it is optimal in the sense that all types 1, 2, and 3 of degrees do appear in the minimal generating set of the Cox ring of a K3 surface. So all of them are really necessary for the Cox ring of some K3 surface. And another thing is that, let me say that we expect that the same idea could work well for other classes of surfaces. For example, when we are looking at the Rieger surfaces, and also we intend to look to weak del Pezzo surfaces. So I don't know if I want to really to go inside the proof of this. I prefer not, because I don't have much time, but I already said before that the key step is this Koszul type sequence with 3 terms. This is essentially the idea of this. So let me go on because I want to talk to you about how we applied this result. And so let me recall this theorem I mentioned briefly before. So what are the Mori-Dream K3 surfaces? I didn't say it so far. So a complex projective K3 surface is a Mori-Dream space if and only if the effective cone, the rational effective cone, is polyhedral, or equivalently, the automorphism group of the surface is finite. The equivalence between these last two properties, the polyhedrality of the effective cone and the finiteness of the automorphism group, is a classically known classical result by work of Piatowski, Shapiro, Shafarevich, Nikulin, and Wimberg. And actually, they also they provided a quite explicit classification of K3 surface satisfy this property. Explicit, actually, in the sense that it turns out that this property, the fact that the automorphism group is finite, depends on the structure of the Néron-Severi lattice of this surface. So the classification consists of a list of lattices. And we know that so a K3 surface is Mori-Dream if and only if its Néron-Severi lattice is isometric to one of them. More precisely, we know that according to the Picard number, so if the Picard number is 1, so the K3 surface is always Mori-Dream. If the Picard number is 2, the surface is Mori-Dream if and only if the Néron-Severi lattice contains a class with square 0 or -2. Observe that there are infinitely many lattices with this property. For Picard number between 3 and 19, there are finitely many Néron-Severi lattices satisfying this property. And so finitely many families of Mori-Dream K3 surfaces, and all Picard numbers are realized. And finally, if the Picard number is 20, we know there are no Mori-Dream surfaces, essentially because we know that there are infinitely many -2 curves, so the effective cone is not polyhedral. So what we did is we tried to apply the result I mentioned before, which kind of bounds the degrees of the generators, and we applied it to some low Picard numbers, actually to Picard number 3 and 4. As I said, starting from Picard number 3, there are finitely many families. And what we proved is that we computed the degrees of a set of generators for the Cox ring of Mori-Dream K3 surfaces for Picard number 3 and 4. And these sets are minimal, except for some of them where we could not decide. So let me show you the result can be described in some tables. For example, for Picard number 3, there are 26 families of Mori-Dream K3 surfaces. And you can see I write BF is the Hilbert basis of the effective cone. It means that these are the degrees of the generator, for example, in the first case, are exactly in the Hilbert basis of the effective cone. E denotes the set of classes of -2 curves. It is always there because I said they are necessary. BNF is the Hilbert basis of the NEF cone. And as you see, there are some cases where we have a lot of degrees. So in general, they are quite complicated objects. And when you see, as I mentioned, when you see an asterisk, it means that we are not sure that a generator in that degree is really necessary. Yeah, this is probably a part of the result which can be improved. And for Picard number 4, actually it turned out to be easier. We only have 14 families. And except for the case 11, 13 and 14, we have the degrees of a minimal set of generators. Observe, for example, the last case, number 14, we know that there are at least 71 degrees which must appear. So it is a very complicated, very big Cox ring. Of course, we didn't even try to compute to find exactly, to compute the ring. Yeah, but we have at least 71 generators. So the proof here so relies on the previous theorem, and it is done with the aid of Magma. Actually, we wrote several libraries in Magma to deal with this. First of all, we implemented Wimberg's algorithm. So we know that there are, actually we learned later that there are other implementation of the algorithm with other softwares. So this library find -2 determines the classes of -2 curves applying a classical well-known algorithm due to Wimberg. And for example, for picker number 4, we found all -2 classes for all families, and this is new. While for picker number 3, this was already done by Nikulin. So of course, this allowed to compute the effective cone, because it is known that in this case, for picker number at least 3, in these cases, the effective cone is generated by the classes of -2 curves. So we constructed the cone, we computed its dual, which is the Neff cone, and then we constructed the Hilbert basis of it, and we took all sums of at most 3 classes there, and we analyzed them using I just say COSUL type tests. So we don't just use the previous one. We have some more sophisticated theoretical results, but more or less they are based on this idea of COSUL exact sequence. And we use this to discard degrees, to filtrate in some sense. This is contained in the library testlib. And finally, at the end, we are able to prove that certain degrees are necessary. So the other way around, now we prove that we do need certain degrees by means of a certain minimality test, which is contained in a different library. For reason of time, I'm not going to explain this. All of these libraries are available in the archive, last archive version of the paper. So I think I just have 5 minutes, right? So I will finish with 2 examples. I think they are quite nice. So there are 2 families of Mori-Dream K3 surfaces of picker number 4. And the nice thing is that geometrically, they are quite a similar description, but from the point of view of the Cox ring, they are very, very different. So the first one is the following family, or let's take a K3 surface whose Néron-Severi lattice is isometric to the one you see there. We computed the classes of -2 curves, and we see there are 6 of them, 6 classes, whose intersection graph is the one you see in the picture. And so we computed the Neff cone, and it is the Hilbert basis of the Neff cone contains 33 classes. And 2 of these classes have self-intersection 0, and define 2 elliptic fibration, which are the only ones on these surfaces. Each of them has just 1 fiber of type A2 tilde. Actually, the 2, you can see the A2 fibers are these 2 triangles. Unfortunately, cannot write on the screen. So you can see 2 triangles, in a left triangle and the right triangle. These 2 triangles are the 2 A2 tilde fibers of these 2 different elliptic fibration. Moreover, you see that there are kind of 3 black segments, E1, E2, E5, E6, and E3, E4. And the intersection multiplicity between A1 and E2 is 3, and the same for the others. And so if you take the self-intersection, for example, of E1 plus E2, you realize that you have a class of self-intersection 2. And actually, this gives this example, and this gives a double cover, 2p2, branch along a smooth plane sextic. And this sextic has three tangent lines. So lines which are everywhere tangents, L1, L2, L3. And this, when you do the double cover, what happens is that each of these lines splits into smooth rational curves, so 2 minus 2 curves intersecting in 3 points. And these are exactly the 3 pairs, E1, E2, E5, E6, E3, E4. So the sum of of them gives, so are linear equivalent. We can give a very explicit defining equation actually in a weighted projective space if you want. And the equation is this x3 square. So this gives a double cover. And the equation of the sextic is the square of a cubic plus F1, F2, F3 times G1. F1, F2, F3 are nothing but the equations of the three lines, L1, L2, L3. And G1 is a cubic. So actually, what happens is that in this case, if one looks at the restriction of the double cover over the union of the three lines, the covering is trivial. So if you leave out, of course, the ramification points, the covering is a trivial covering. Actually, if you see the for example, E1, E4, E6 is a copy upstairs in the K3 surface of the three lines downstairs. So there are three smooth rational curves, intersecting in that way. And the same for the other triangle. And in this case, it turns out that we can say everything about the Cox ring. So we know that there are exactly 8 generators. So not just the degrees, we have exactly 8 generators. 6 of them are the elements defining the -2 curves. And we have 2 more, which define smooth fibers of the 2 elliptic fibration. This is due to the fact that the elliptic fibration only had one reducible fiber. So we need one more generating element to generate the H1, essentially, of the class. And moreover, if we take a very general K3 surface in the family, we can explicitly give a presentation for the ring, which is this one. Well, it is actually a complete intersection. And we have 2 relations, which are the one I give here. And I'm not going to details, but this G1 tilde, G2 tilde come from the G1 and G2 in the equation I gave before. So this example is, I would say, we can understand it very well. Let me give a second one, which is quite, in some sense, similar. So now the lattice is this one. Again, there are 6 -2 curves, but this time the intersection graph is different. It's this one. But again, we have these pairs intersecting with multiplicity 3. And actually, as before, there is a double cover, branch along a smooth plane sextic with 3 tangent lines. And again, the class is given by E1 plus E2. But here, first of all, there are no elliptic fibration. The Hilbert basis of the NEF cone contains, in this case, well, 39 classes. And what happens is that we can kind of identify the degrees of the generators of the Cox ring, but we cannot identify them geometrically. Well, we know there are the 6 classes of the -2 curves, but then we have these classes H1, H2, H18 are classes in the Hilbert basis of the NEF cone. We know they are non-hyperelliptic with self-intersection 4, some of them, 26, some of them, and 28, some of them. We cannot really explain this, and we cannot compute the ring. And also we cannot say how many generators are there in each of these degrees. So it's geometrically, they are similar, but the Cox ring turns out to complicate much more in this case. So even if we are working with a class of surfaces, which is well understood from the point of view of linear system, etc., we still can have surprises for the Cox ring. So I think it's still interesting to be investigated. And this is all I wanted to say. So this is just some bibliography.
Thank you very much, Michela. We thank you. Clapping. And there is some time for questions or comments.
Sorry, I had another question. Michela, can you go back to the main theorem?
Yes.
Oh, yes. My question was just this. Which properties of the K3 surfaces are you using? The description of the NEF classes, right?
this property here, I
This
record
property,
here.
yes.
So the fact that we can control the H1 of an F divisor essentially up to some exceptions. And also the fact that we are the same for the base locus. These two, the first two properties in this page, I would say, they are fundamental in the proof.
So so the nefness and the base locus, right? And the H1.
Mm-hmm. Well, I can show you actually, well, there is also this property on the H2, which probably, but essentially would say the vanishing of the H1 is the...
So you have the surjectivity in the Kotzul type.
Exactly.
Yeah. Okay, thanks.
You're welcome.
I was thinking, I had the same question as Gilberto. I was wondering, these two theorems you were showing at the beginning are a main ingredient, because you say a lot about magma, but each time you use this vanish of cohomology to have the surjectivity, and then so you can eliminate some generators.
Exactly.
Yeah, yeah, that's right. Okay.
Yes, this proposition here essentially.
Yeah.
So at least for this theorem, this is more or less the key point. Yes.
And I have another question. If one want to do a similar result, to get a similar result for Picard number 5 or higher, so where is which one among the steps of the proof of the theorem is getting difficult? So the computational part, or the number of degrees appearing, say?
I would say the computation, just the computational part. Everything is the same. Only I think, yes, I'm not sure if the libraries works. So sometimes the computation could not end, for example. So just the computational part. There are no, I would say there are no other theoretical aspects, no new aspects. Mm-hmm.
Okay, thanks. So are there other comments or questions to Michela? Otherwise, we can thank you again, Michela.
Thank you.